Inductance of a three-phase overhead line for balanced, symmetrical spacing. Generally, symmetrical spacing is in the sense three conductors, A conductor, B conductor, C conductor, are having a same or put in same distance, small d. Suppose A to B distance is D1, B to C D2, C to A D3. For symmetrical spacing, D1 equal to D2 equal to D3 equal to D. That's why we have to determine the first of all flux linkages of A. Flux linkages of A means so internal flux linkage of A and mutual flux of B conductor, C conductor, right? Suppose we have to derive the flux of B means internal self inductance of self flux linkages of B conductor and mutual flux linkages of A and C. Like that, we have to initiate one conductor. That conductor produce self flux linkages. Remaining two conductors may produce mutual flux linkages. We consider all self of A, mutual of B, mutual of C. Like that, you have to derive pi A, pi B, pi C. Pi A is equal to mu 0 IA by 2 pi 1 by 4 plus log E d by R. Similarly, pi B plus pi C. So L means LA is equal to pi A by IA. IA cancelled mu 0 by 2 pi. What is the value mu 0 by 2 pi? 2 into 10 power minus 7, right? 2 into 10 power minus 7, 1 by 4 log d by R. So that may be approximately 2 into 10 power minus 7 log d by R dash Henry per meter. This is the derivation for symmetrical spacing. We have to find out the symmetrical spacing. Current IA plus IB plus IC equals 0 because of balanced one. Look at the picture A, B, C only. A, B, C only. D, D, D. Distance is D, D, D. And flux linkages 2 into 10 power minus 7 IA ln d by R dash. Flux inductance of A means IA cancelled. 2 into 10 power minus 7 ln d by R dash. Like that. Total flux linkages, this one. Like that, you have to derive the inductance of LA is equal to 2 into 10 power minus 7 ln d by R dash. Now go for the asymmetrical spacing. Now, today class, we discuss about the derivation of inductance, three-phase inductance for asymmetrical spacing. When three-phase line conductors are not equidistant from each other. So, three conductors అనేవి ఒకే డిస్టెన్స్ లో లేకపోతే దాన్ని మనం అసిమెట్రికల్ స్పేసింగ్ అంటాం. త్రీ కండక్టర్స్ అనేవి ఒకే డిస్టెన్స్ లో ఉంటే దాన్ని మనం సిమెట్రికల్ స్పేసింగ్. లైక్ దట్ వెన్ ద త్రీ ఫేజ్ లైన్ కండక్టర్స్ ఆర్ నాట్ ఈక్విడిస్టెంట్స్ from each other, then the conductor spacing is said to be unsymmetrical spacing. So under such conditions, under unsymmetrical conditions, flux linkages and inductance of each are not same. So flux linkages and inductance both are not same. A different inductance in each phase results an unequal voltage drop in three phases. Right? A different inductance in each phase may result unequal voltage drop in three phases RYB. Even if the currents in the conductors are balanced, currents are balanced, IA plus IB plus IC equal to 0. Even though IA plus IB plus IC equal to 0, but voltage drop are not same because of unsymmetrical spacing. Why? So inductance are not saming. Why? Distance are not saming. So distance will be differ such that inductance flux linkages differ, inductance differ, voltage drop also differ, right? Therefore, voltage will not be the same for all phases. In order that voltage drop are equal to all conductors, we generally interchange the position of the conductors at regular intervals along the line. You understood? So whenever asymmetrical spacing is considered at the situations, voltage drop are not same because of inductors are not same. Suppose we are getting Inductance are same or voltage drop are same. Transpose the conductors. Interchange the conductor. Suppose in one line A, B, C, in another line B, A, C, in another line C, A, B, like that. We have to interchange the transmission line such that we neglect the or we are getting the equidistance or equi inductance. So the original position of every other conductor over a equal distance, such as exchange on position, is known as transposition. 2 marks important. What is transposition of a transmission line? So to change their position of each conductor, that means they occupies their original position of every other conductor. So this exchange of position of conductors is called as transposition of conductors, right? So, so this is look at the picture. A, B, C. Suppose one conductor, second conductor, third conductor. Line 1, line 2, line 3. A conductor, B conductor, C conductor. Now, after some distance, we have to transpose the. So at first distance, C will be lower, A will be upper. Now C will be go to the lower upper, A will be go to the middle, and B will be go to the last lower. Now after some distance, B will goes to the upper, C followed by C followed by A. So this is nothing but transposition of transmission lines. So to get the equal distance, such an exchange of position is known as transposition. Look at the figure. Three-phase conductors are designated as A, B, C. At their positions occupied are numbered as 1, 2, 3. Figure shows A phase transposed line of unsymmetrical spacing. Let us assume that each of the 3 sections in the 1 meter length. So now I am taking a calculate the inductance of A phase only, not B and C. Why? Because both are same. So all are same. That's why I am calculating this one. And the the distance must be 1 meter length. So we know that whenever you have to transpose the conductor transmission conductors or does not transpose these transmission conductors. So suppose it is a symmetrical balanced current IA plus IB plus IC equal to 0. So even though asymmetrical also IA plus IB plus IC equal to 0, right? Current is balanced but voltage drop different. That's why we are doing transposition of transmission lines. So by using this one, we can reduce the telephonic interference also. That is the good important question. How to reduce the radio interference in transmission lines by transposing the transmission lines. Let us consider balanced current IA plus IB plus IC equal to 0. Now IA having, suppose I am considering this IA, it is 3 phase. IA is nothing but magnitude IA, phase angle 0 degrees. IB, I at an angle minus 120 degrees. Sorry, 120 degrees. IC, I at an angle 240 degrees. Right? So 3 phases are displaced to 120 degrees to each other, and we can represent currents and conductor A current as the reference. That's why current A conductor is equal to total current I, magnitude current I at an angle 0 degrees. IB, I at an angle 120 degrees. IC, I at an angle 240 degrees. Right? And we know we already derived last one. Our first section, flux. This is the self and these two are the mutual, right? So IA itself, self inductance, and these two are the second position mutual inductance on first position, third position mutual inductance on first position. Mu0 I by mu0 by 2 pi IA into ln 1 by r dash IB into ln 1 by from this onwards to this onwards distance is d12. So d1 d2 d12 plus IC ln D13 or D31, whatever it may be. Similarly, for second section, 2 into 10 power minus 7 IA ln 1 by RA dash IB ln D23 A. Why? Because here second position A is there, but in first, look at carefully. Look at carefully. For first position, A is the top, remaining 2 is the followed by remaining 2 conduct. That's why IA ln 1 by RA dash, IB ln 1 by D12, IC ln 1 by D13 or D31, whatever. Now coming to the second section, here top is the C, but I am taking reference as A. You have to write down the flux linkages equations according to A. But at second section, what is the second A position? It is a second conductor. That's why 2 into 10 power minus 7 IA ln 1 by RA dash from this to this. So IB, so like this IB, so ln 1 by D23. A position is second now, D23. Next IC ln 1 by D21 or D12, whatever it may be. Now coming to the third section. Third section. Here the position of A is third. Third. So pi A3 or lambda A3 equal to 2 into 10 power minus 7. IA ln 1 by RA dash plus IB. So what is the distance from A to B? Here A is the third position. That's why A3 1. A3 1 by D13 or D31 plus IC. So 1 by D32 or 23, whatever it may be. Now these are the fluxes of um, first section, second section, third section. Now taking the average average values. Pi A or lambda A is equal to pi A1 plus pi A2 pi A3 by 3. Otherwise, lambda A1, lambda A2, lambda A3 by 3. Right? So substitute the values. We are getting like this. IA must be common. 3IA by 3 cancel. That's why IA into ln 1 by RA dash plus IB D12, D23, D13 whole power 1 by 3. So IC D12, D23, D1 power 1 by 3. So from the balanced current equation, IA plus IB plus IC equal to 0. That is IB plus IC is equal to minus IA. Right? Substitute that one and we are getting the pi A or lambda A is equal to 2 into 10 power minus 7. IA ln D12, D23, D31 1 by 3 RA dash. Suppose symmetrical spacing or equilateral spacing, D12, D22, D31 equal to D capital D. So D cube whole power 1 by 3, cube whole power 1 by 3 cancel, D will be remaining, right? So before for symmetrical spacing, 2 into 10 power minus 7 ln D by R dash. But now coming to the asymmetrical spacing, 2 into 10 power minus 7 ln D12, D23, D31 by RA dash whole power 1 by 3. So from that inductance, IA cancel, 2 into 10 power minus 7, D equivalent by R dash. D equivalent means that one. Suppose it is a equivalent spacing, D by R dash only. So sometimes some textbook where write down 2 into 10 power minus 7 ln D equivalent by ds, otherwise dm by ds, gmd by gmr. 2 L is equal to 2 into 10 power minus 7 gmd by gmr. Like that we have to write down the equations, right? So this is the unsymmetrical spacing, three phase unsymmetrical spacing derivation. So same D12, D23, D31 for unsymmetrical spacing. These three distances are not same. For symmetrical spacing, these three distances are same. So there is no neutral wire. That's why IA plus IB plus IC equal to 0. Why there is no neutral wire? It is a transmission system. In distribution system only neutral wire is available. In transmission system, three wires, three phase, three wire system, right? That's why IA plus IB plus IC equal to 0. Look at the picture, just your observation only. Derivation is completed. How we are transposing the transmission lines? So it is a communication line, right? This is a telephonic tower. So through the telephonic tower, the power lines also carrying. At that time, radio interference or communication interference will appears. To reduce that one, so we have to transpose the positions of conductors. So year 1, year 3, year 2, year 1, year 3, year 2, and after some distance 1 2 3 3 2 2 3 1 3 1 2 like that. So high voltage transposition lines. Same derivation. Single versus double circuits. Look at this is the single circuit, single earth wires, and double circuit, single earth wires. Tower. So three. These are the cross arms. Three cross arms, two cross arms, one cross arm, and here like this. We don't have that double circuit line, but in gate itself, double circuit line will be there. And suppose the given double circuit line like this. So as usual, determine the A. From A, you have to determine what is the AC distance, what is the AB dash distance, what is the AA dash distance, like that. And find out GMD, DAB, DBC, DCA all power 1 by 3. All are same, so it is DP. All are different, it may be a like this. So generally, double circuit line means so consists of two parallel conductors generally. Self GMD of the conductor is R dash is equal to 0.7788 R. And self GMD for A dash conductor. Look at the picture. A dash conductor, self GMD. And self GMD of AB dash, self GMD of AC dash. And AB AC. Like that you have to determine total. Self GMD of AA dash is, first of all, distance between the AA, DAA. Next, DA to A dash, D A dash, A dash, A dash A dash A dash. So whole power 1 by 4. Similarly, from B, self GMD of BB dash is DS2. So you can suppose DS2 for section 3 you can consider as B, that is consider as DS2. DS2 is equal to DBB dash DB dash B dash B dash. So observe it, BB distance from itself, BB B dash B dash DBB D B dash B dash D B to B dash D B dash to B whole power 1 by 4. Similarly, section 2, that is DS3 DCC into DCC dash DC dash C DC dash C dash whole power 1 by 4. Now we have to determine individual self GMD. Now combine the all GMDs. DS is equal to DS1, DS2, DS3 whole power 1 by 3. Whole power 1 by 3. Like that you have to determine the self GMD. Now how to determine the mutual GMD? DM1 is equal to AB, DAB, D A dash B dash, D A dash B, DM1 or DAB is equal to DAB, D A dash B dash, D A dash B and D A B dash. Similarly, DBC, DBC, DB dash C dash, DB dash C, DBC dash whole power 1 by 4. Like that, DCA also DCA DC dash A dash plus DC dash A DCA dash whole power 1 by 4. Now you have to determine overall GMD. GMD is equal to GM1 into DAB plus DBC plus plus not plus DAB multiplied by DBC multiplied by DCA whole power 1 by 3. So DM is same for all three phase if conductor having same radius. Otherwise you have to calculate. Like that you have to determine the GMD GMR in double circuit also. But we don't have syllabus. So look at your first unit syllabus. You have completed type of conductors, completed the calculation of resistance, skin effect, internal external flux linkages, inductance single phase, flux for a group, inductance for composite, inductance of three phase symmetrical asymmetrical, right? And inductance of double circuit also you have to complete. Now you have to go for the problem in inductance. So like that, suppose in problems like that you have to calculate the self GMD, that is GMR. Suppose only two conductors are there, DS is equal to, so you have to consider, you have to assume this conductor. So from this conductor to this conductor distance is D and self distance is R dash. Whole power here two conductors, that's why 1 by 2. Suppose like this symmetrical spacing D. I am assuming this one self distance is R dash and from this conductor to this conductor distance is D, this conductor to this conductor distance is D, that is D into D square whole power 1 by 3. Suppose like this, self is R dash and this conductor to this conductor distance is D and this to this D, but this conductor to this conductor, so that is the Pythagoras Siddhantam. So hypotenuse square is equal to adjacent square plus opposite square, D square plus square root of D square plus D square, that is root 2 D. So that's why R dash root 2 d square, here d cube whole power 4 conductors, that's why 1 by 4. Like that you have to determine the self GMD. So these are the bundle conductors. Spacing between the bundle conductors is 0.4 meters and distance, overall distance is 7 meters. Bundle conductor, these two are the bundle conductors, spacing with 0.4 meters, right? From these conductors, another conductor A dash conductor, B dash is 7 meters, like that. So overall formulas: inductance single phase 2 into 10 power minus 7 log dm by ln dm by ds. Dm means so spacing between the conductor, d by r dash, right? Formula for single phase 2 into 10 power minus 7 ln d by r dash. R dash means 0.7788 r. Three phase line 2 into 10 power minus 7 ln dm by ds. Dm is nothing but d1 d2 d3 whole power 1 by 3. If it is symmetrical, d cube whole power 1 by 3, that is cube. Only dm is equal to d for symmetrical. For asymmetrical, d1 d2 d3 whole power 1 by 3, right? And ds is always r dash, that is 0.7788 r. So you have to remember these two formulas for solving the problems. Single phase inductance for conductor per meter is 2 into 10 power minus 7 ln d by r dash. For three phase 2 into 10 power minus 7 ln dm by ds. Dm is nothing but d1 d2 d3 whole power 1 by 3. For symmetrical spacing, the value is d. For asymmetrical spacing, value is like this. Always symmetrical or asymmetrical, ds is 0.7888 r, right? And double circuit, this is the formula. So go for the problem. A single phase transmission line. So this problem is already done, na? Sandhya? Problem 1 is already solved, sir, in last classes.
Okay,
This,
sir.
this problem already solved in last class, right? 2.38 millihenry loop inductance. If it is a copper, do you remember? గుర్తుందా మీకు? ఆ రోజు నేను చెప్పాను. కాపర్ అయితే రిలేటివ్ పర్మిటివ్ 1, స్టీల్ కి అయితే 100. So once again you have to listen, no problem. A single phase transmission line has two parallel conductors 3 meters apart and a radius of each conductor being 1 centimeter. Calculate the loop index per kilometer, and the material is copper, steel. They don't given relative permittive, put 1. They given, the value is taken. So loop inductance is nothing but formula. So L into 2 into 10 power minus 7, sorry, 10 power minus 7. I am giving one formula, 10 power minus 7 1 by 4 plus so I am giving one formula. Loop inductance per meter equal to 10 power minus 7 mu r plus 4 log d by r Henry per meter, right? ఆ ఫార్ములా చెప్పాను నేను. అది లూప్ ఇండక్టెన్స్ పర్ మీటర్ ఈక్వల్ టు 10 power minus 7 mu r plus 4 log d by r Henry per meter. ఆ ఫార్ములాతో చేసాం మనం. మీరు అదే ఫార్ములా యూజ్ చేసుకోండి, ఇది వద్దు, ఇదైతే మళ్ళీ కన్ఫ్యూజ్ అవుతుంది. ఓకేనా? Next class, I will continue next class, ma. Next problems, remaining problems, I will continue next class, right?
Yes,